Okay, we're going to get started on section 5.3. The title of this section is Wilson's theorem. And basically this is it. That's all we're going to do in this section is prove one important theorem that actually gives a primality testing for integers, means give a necessary and sufficient condition for an integer to be a prime. Unfortunately, it is not practical, as we're going to see from the statement. Then we're going to look at examples. In fact, I want to first illustrate the proof of Wilson's theorem through an example, all right, and then give some other examples later on. Then we're going to look at an application of Wilson's theorem to provide a necessary and sufficient condition for the solvability of this special quadratic congruence equation x squared is congruent to -1 mod p, where p is a prime. All right, let me get started with actually a lemma first. All right, this is the technical lemma that we need. And it reads like this, let p be a prime. And k is an integer between 1 and b minus 1. Then k squared is congruent to 1 mod b if and only if k is equal 1 or k equal p minus 1. All right? And so what does this statement actually means? That is, the only integers that are inverses. Now actually, let's say the only integers in this integers k between 1 and b minus 1 that are their own inverses are k equal 1 and actually inverses mod p. Mod p are k equal 1 and k equal p. Well, what does this mean when we say this is k squared is congruent to 1 holds for k equal 1 means it is 1 times 1 is the identity, which we of course know that for actual numbers, but here is the other possibility is k is equal to p minus 1. So when you square that, you come up with 1, which means that p minus 1 times itself is equal to an identity in some sense. All right, actually this is the identity in the, as I say, if you know a little bit of regular arithmetic, so this is this ring. All right, so it is only two numbers basically for integers mod p are 1 and p minus 1 are their own inverses. All right, so we're going to go ahead and prove this. This is an if and only if. So let's start with assuming that going this way, the easy direction. if k is equal to 1, then definitely when 1 squared is equal to 1, and this is congruent to 1 RP. And if k equal p minus 1, then p minus 1 squared is equal to p squared minus 2p plus 1. And the multiples of p, they're going to be congruent to 0 mod p, so we end up with 1 mod. All right, let's go the other way around and assume that actually the congruence holds. Let's go in this direction. Assume that k is between 1 and p minus 1, and k squared is congruent to 1 mod p whole. So we have a correct congruence relation. Well, this implies that p is going to be dividing k squared minus 1, which is equal to k minus 1, k plus 1. Since p is a prime, then it's going to divide either one of these. So this implies p divides k minus 1, or p divides k. All right? Now, let's take the two possibilities. This implies that k minus 1 equals pr, or k plus 1 equals ps for some r s n z. All right? And again, this allows us to write that k is equal 1 plus PR, or in here k is equal to ps minus 1. All right, now we have, of course, k is between 1 and p minus 1. So if I subtract 1 from this, probably we need to use the k minus 1 in here. So this becomes 0 less than or equal k minus 1 less than p minus 2. All right? Now, since we have the so now we, let's see here. So we have a k minus 1 is between 0 and p minus 2, and we have also the k minus 1 is equal PR. All right, so multiple of r. And the only way this could happen that k minus 1 is a multiple of p, but at the same time it is smaller than p minus 2, which is of course smaller than p. All right. This implies that k minus 1 must equal to 0, and this implies k is equal to 1. So this is if the first scenario happens, then k is equal to 1. Similarly, if we look at this case, we have again k between 1 and p minus 1. Let's add 1, so we get 2, so equal k plus 2 less than or equal to p. All right? And since k plus 2 is a multiple of p, and in order for this to happen, the s in here must actually equal to 1. And also we have And since k plus 1 is equal to ts, so these two inequalities implies that k plus 2, let's see in here. Actually, k plus 1, I'm sorry, k plus 1. I'm just adding 1. All right, so k plus 1 must equal actually to p. All right, and with that, this means that the k is equal to p minus 1. All right, so therefore, we have the result. All right. Now, so the net conclusion is therefore that k squared congruent to 1 mod p holds for k equal 1 and k equal p minus 1. So these are their own inverses. Then this would imply then for the other values of k, where k is between 1 and p minus 1, namely 2, 3, 4, and so on, up to p minus 2, if they have inverses, actually you're going to see they do if they have inverses. Then it must be different than the number itself. All right. So this is a big F in here, which we're going to see, yes, in fact, it is. Means that you look at the inverse of 2, it's not going to be 2, it's going to be one of the other numbers. It's really the same thing. All right? So before we actually state, let me actually state Wilson's theorem, and then we're going to illustrate the method of the proof that we're going to use by an example. All right? And then we will give the formal proof. All right, so Wilson's theorem. Actually, there are two parts to this. It's an if and only if, but I'm going to separate them into two different theorems. This is 5.4. And called Wilson's. Actually, this is the part that Wilson's stated, without a proof, okay? But later on, it turns out the converse of the statement that Wilson's made is also true. Let P be a prime, then p minus 1 factorial is congruent to -1 mod p. Okay, so let's illustrate this by an example. Okay, so this example, we're going to kind of follow through the steps that we're going to use in proving the theorem. Okay, so let's take p equal 30. So we're going to make a list. All these numbers. One, two, three, up to p minus 1, which is actually 13 minus 1. Okay? In this list, has 1 and 12 are their own inverses. Well, let's check. Well, what does it mean for, and two elements, okay? So let's look, actually, definition here, 2 inverses mod 50. All right? So it's very simple to say what does it mean for 2 elements to be inverses? A and A prime, okay? And these are between 1 and p minus 1, which is a complete residue system mod p, all right? Are inverses mod p, does say in general, if A times A prime is congruent to 1 mod p. Just exact same like actual numbers, real numbers being inverses, when you multiply it, you come up with 1. So now we can check this, of course. We prove this is in the lemma 1 squared is congruent to 1, of course, mod 13, and 12 squared, all right, which is 144. Is this congruent to 1 mod 13 or not? All right, so this is 143, and 143 actually is divisible by 13. I don't know what it is. If you multiply this by 13 times, I didn't do the calculation in here, but I believe this is the case. Let's see if I try 5, 3, 6. Yeah. Well, just gonna leave it for. All right. So I haven't figured out the number in here. All right. So now the other numbers. It turns out that every number is going to have a different number as its inverse. And so let's see that what are the inverses of these numbers, which again we're going to do this one in general. So we're going to find in here that so in other words, now we have these numbers. So if I, in other words, remove this from the list, and remove this, then we end up with, there are 10 numbers left, and we can actually put these in pairs. Each number, we're going to put it with its inverse, all right? So we're going to see that these are the inverses. 2 and 7 are inverses for each other. Odd 30, all right? Similarly, we're going to see 3 and 9. Same. Then we have 4 and 10. 5 and 8, and 6 and 11. So this counts for all the numbers in this list with, omitting the 1 and the 12. Now, when we're going to look at the product of these, so if I take 2 times 7, this is going to give me 1 mod 13, and then take a 3 and 9. In other words, rearrange the product, 4 and 10, and 5 and 8, then 6 and 11. Each one of these, again, give us 1 mod 13, so their product is going to be this. Now, if I multiply this by 1 and 13, actually we want to multiply this is by 12, not 13. So which means I'm going to multiply this other side just by 12. So we have this congruence relation for the products. So we have, and now I could rearrange these in, actually let me put them like this. So 7, all right, and 3, 9, and 4 times 10, 5 times 8, and 6 times 11 times 12. So this is congruent to 12 mod 50. However, the product on the left-hand side is nothing but, if I arrange it to becomes 1 times 2 times 3 up to 12, and this is equal to 12 factorial, which is the same as 13 minus 1 factorial. And this is congruent to 12 mod 13. But 12 mod 13 is congruent to negative 1 mod 13. And this is exactly what we need to show, or Wilson's theorem actually claims. All right, so the key idea in the proof in here is to pair each number with its inverse. And it turns out that, as I mentioned, that the only number that there are inverses is 1 and p minus 1, and all others we're going to show they're going to have an inverse that is not their own. All right, so we're going to proceed now to the proof of Wilson's theorem. All right, so here's the proof of Wilson's theorem. All right, so it's very straightforward. First of all, let's take care of 2 special cases for p equal to 2 and p equal to 3. So we have p minus 1, which is equal to 2 minus 1. We put factorial. This is equal to 1, and this is of course congruent to negative 1 mod 2. So in other words, the statement is true. For 3, we have p minus 1 factorial is going to be 3 minus 1 factorial, which is just 2. And this is again congruent to negative 1 on 3. So for these 2 cases, actually the congruence holds. So now we're going to consider the set of integers. We're going to consider actually p is bigger than 3. Okay, so let B be a prime. And then B bigger than 3, B A prime now. And we're going to consider this list. One, two, three, up to P minus 1. And then we're going to let A be any one, be any number in the list. So I'm going to run it through every number in the list. And then we're going to consider the linear congruence relation. Equation, which is AX is congruent to 1 mod P. Now, since A is between 1 and P minus 1, then the greatest common divisor of A and P is equal 1. So this implies that the equation, so this implies AX congruent to 1 mod P has a unique solution. Has a unique solution. All right? This is a sufficient condition for solvability of linear congruence equation. Is the greatest common divisor to be divisible by 1, okay? Which is the right-hand side of the congruence equation. Of course, in here it does hold. All right. Now, by the lemma, we have the solution for when A is equal to 1, or A is equal. Okay, so we're going to here by the lemma. So we have let me call the solution, in other words, before we make this statement. So, so we have AX congruent to 1 mod P as a unique solution for every A in that list. Let us call the A solution, or let's denote a solution that corresponds to A. Let us denote the solution, so it's unique, by A prime. So this means we have A prime is congruent to 1 mod P. Satisfy the equation. So the question is, which we have the only two elements A in the list where A prime equal A, or A equal 1, and A equal B minus. All right? So in this case, we have the A, when A is 1, all right, then the A prime is 1, and we have the congruence holds, and also this is holds for when A is B minus 1. All right. Now, for all others, for all other values of A that does not equal to 1 or B minus 1, A prime is different than A. All right? And we know that they're gonna actually for every A there is an A prime. Okay, so the existence of this multiplicative inverse, all right, part B actually does exist. So we're gonna actually omit these two numbers that there are their own inverses. So we omit 1 and B minus 1 from the list. To obtain this. 2, 3, up to B minus. In fact, there are this as B minus 3 elements. All right? So we're going to group each A with A prime, all right, so that A times A prime is congruent to 1 mod P. All right? So this give us a P minus 3 over 2 pairs of numbers A prime, and these are different, all right, such that again A times A prime is equivalent to 1 mod P. Now, if I do this, when I group these together, okay, I unfortunately I cannot write them like I did with 13. Okay, when we did that, we could put the 2 with the 7 and the other numbers, and here I cannot do this one in here. But what I end up with is 2 times 3 and so on up to B minus 2, because each number, when I group it with the inverse of it, it's going to give me 1, so their product is going to be congruent to 1 mod P. All right, now we need to multiply the two sides of this congruence relation by 1. Of course, not going to do any effect, and P minus 1. To make the left-hand side is actually P minus 1 factorial. All right? So now we multiply this by just basically P minus 1. So we get 2, well, also 1, if you want, 3 up to P minus 2, P minus 1 is congruent to P minus 1 mod P. But P minus 1 is congruent to -1, because if you take the difference between p minus 1 plus 1 here, it becomes p, and this is divisible by p, mod p. And we are done. So this is what actually the theorem is saying. All right. Let me illustrate give another example. All right. Of Wilson's theorem. I want to show that if you take the product of any two 10 integers, none of them is divisible by 11, then their product is congruent to -1 mod 11. All right? So here is the example. I'm going to show that the product of any 10 consecutive integers none of which is divisible by 11 is congruent to -1 to -1 mod 11. We know this is, of course, true for the numbers from 1 to 11 minus 1, which is 10. Okay, this is just Wilson's theorem. Now, this is a little more general. It says that, these numbers doesn't have to be from 1 to, to 10. It could be actually any 10 consecutive numbers. And to prove this, let's assume the first number. Assume that the numbers are, well, k, to start with, positive, negative, doesn't make any difference, k plus 1 up to k plus 9. Okay? So there's 10 of these. All right? And we also know that k plus I is not congruent to 0 mod 11. Means this one is not divisible by any of them. For every I equals 0, 1, up to 9. All right? Now we're going to use the division algorithm to kind of get back to the numbers that we know that they satisfy Wilson's theorem. By the division algorithm, I can write each one of these, k plus I is equal to q sub I times 11, or 11 q sub I, plus r sub I, where r sub I bigger than or equal to 0, less than 11, or less than or equal to 10. Now I claim that the r sub I, all right, actually cannot equal to 0. So we will end up with the possible values is going to be from 1 to 10. Okay? And claim that Ri not equal to 0 for every I from 0 on up to 9. Well, if it is equal to 0, of course, if I equal to 0, this implies that k plus I is going to be a multiple of this, but this is, of course, a contradiction. All right? So, therefore, we have k plus I is congruent to R sub I. So, before I do this one, so the possible values of the remainders so this implies R sub I is going to be less than or equal 1, less, and this one less than or equal to 9. And this is for every I from 0 to 9. All right. So now, what we have k plus I is going to be congruent to R sub I, and mod B. And now the product of all of, and then also we have, of course, Ri is between 1 and actually the Ri 10. I'm sorry. This one is supposed to be 10. This is less than or equal to 10. So I have actually 10 values in there. And now the product of these, we take the product, I equal 1. Let me make this 0 actually. To 9, this is going to be congruent to the product of the R. I equal, actually we could go from I to 10. That make any difference in here. Let me put actually this is 0 to 9. All right. Now anyway, so this product is going to be actually 10 factorial, and this is congruent to -1 on. All right. Now let's look at actually the converse of Wilson's theorem. It actually happens to be true. It says that if n is an integer such that n minus 1 factorial is congruent to -1, then n is a prime. Okay? So here's the theorem. So this is called converse of Wilson's theorem. And state that let n be a positive integer such that n minus 1 factorial is congruent to -1 mod n. Then n is a prime. It would be a very nice theorem if we can actually use it to show a certain integer is satisfy this condition. Now you can imagine if you take actually n is equal to, I don't know, 7, for example. So what you have to do, you need to do 7 factorial. All right, calculate 7 factorial and check this congruence. As you see, the factorial it grows so big, and that it is not feasible to calculate the factorial of a number that has 100 digits in it. Okay, so this is not, it's for theoretical reason it's fine, but it's not a practical test for the prime element. All right, actually the proof of this is very simple. So we're going to assume that the contrary, okay? So we're going to assume that n satisfy this congruence relation, but n is composite. So this implies that there exists a divisor that divides n such that d is bigger than 1, less than n. Okay, so there's a proper divisor of n. Now, this congruence, we can write it as a divisibility condition. So we have n minus 1 factorial is congruent to -1 mod n, implies n divides n minus 1 factorial plus 1. We also know that we also have d divides n. Then we can use the transitive property, d divides n, and n divides n minus 1 factorial plus 1 implies d divides n minus 1 factorial plus 1. All right. Now we need to take a combination of these two, okay, and say that d divides. So we're going to take these together, all right. Actually, one other thing we can also conclude that d is going to be among the numbers that are in the factorial. One other divisibility we need, since d is less than n, or this is less than or equal n minus x, the other way around. So this one implies d actually could be less than or equal n minus 1. This is bigger than. So, and this means that the d is going to be one of the factors. Then d is one of the factors in n minus 1 factorial. Because remember, this is 1 times 2. Somewhere there's going to be a d, okay, up to n minus 1. So which means that this implies d divides n minus 1 factorial. Now we also just have shown, we also have d divides n minus 1 factorial plus 1. So this is this congruence right here, or this divisibility. So we can say that d divides a combination of these. And this combination I'm going to take as 1 times n minus 1 factorial plus 1. minus 1 times n minus 1 factorial. And the difference between these is equal to 1. So this implies d divides 1. Well, this is a contradiction because the only way this could happen means d is equal to 1. Okay? So d equal to 1, but we assume d does not equal to 1. All right? All right, now, Wilson's theorem together with its inverse, again, provide a necessary and sufficient condition for an integer to be a prime. So we could state this in one theorem to reflect this fact. All right, so we have this is an integer. N is, actually we say a positive integer. There's n bigger than 0 is prime if and only if the congruence n minus 1 factorial is congruent to negative 1 mod n holds. All right. We look at one application of Wilson's theorem to the proof of or give a necessary and sufficient condition for a congruence equation to have a solution. So this is theorem 5.5. All right, and it reads like this again. Let P be a prime. Then the quadratic congruence equation x squared congruent to negative 1 mod p has a solution if and only if, you see here, not indicate, if and only if P is equal to 2 or P is congruent to 1 mod 4. And remember this condition, we can say that it's equivalent to that P is equal 4k plus 1, where k is actually in zeros. Okay? It has this form. All right, let's start it with assuming that P actually has this form or this form and show that the congruence has equation. Okay? Then we're going to go this way. So if P is equal to 2, then actually x equal to 1 is going to be a solution. Is a solution. Now we can do this one just by checking. Because 1 is squared is equal to 1, and this is congruent to negative 1 mod. All right. Next, let's assume that P is equal to 4K plus 1, all right, for some K in Z plus. And of course, it's a prop, so that this one is this form, and P is a prop. So remember that not every number of this form is a prime. Some of them are prime, some of them are not a prime. All right. Now this is what I'm going to do. I'm going to look at the P minus 1 factorial. That is what we have in Wilson's theorem. And we're going to examine the product, the factors in this product. Or you're going to consider this P minus 1 factorial. All right, I want to write it out. Okay, so this is equal 1, 2, up to, actually, we put a J in here, and this is P minus 1 over 2. So this is the first group of the product, and then the next number to this is P plus 1 over 2. Then the next one up to P minus 1. All right. Now we're going to see, let's actually consider an example. So if we take P is equal to 13, all right, so there are actually in here 11 numbers, and the middle one, all right, which is the P minus 1 over 2, it's going to be 6, right? So when I write this, write it as 1 times 2 up to 13 minus 1 over 2, then so this is going to be 1 times 2 up to 6. So this one is going to be actually P plus 1, that's 14 over 2, this would be 7, and so on. So you could see that actually up to 12. One other thing you will notice in here, that the 7 is also equal to 13 minus 6. Then the next number is going to be 13 minus 5, and so up to 13 minus 1. In other words, these numbers in here, each one of them is going to be actually the P minus J. All right? So altogether, this means I can write this as a product of J for these, and this is J is equal 1 up to P minus 1 over 2. And then this is the other half of the product, and this is P minus J. All right, and I know this one by, of course, by Wilson's theorem. This is congruent to -1 mod P. This is by Wilson's theorem. Well, let's look at actually this factor in the product, and so let's look at this J times P minus J. So this is equal to JP minus J squared. Now mod P, JP is congruent to 0, and so this becomes minus G squared mod P. All right, well, let's put this in the product and see what it would be. So now let's consider the product. J equal 1 to B minus 1 over 2. All right, so it is J times B minus J. This is congruent to negative, the product, first of all. This is just a single term, single factor. So this will be the product of J equal 1 to B minus 1 over 2, negative J squared. Now, so we're going to multiply negative 1 squared, negative 2 squared, and so on, okay, up to B minus 1. That's really what that is. And we can take the negative out, all right, and we're going to put mod, because that's what we're going to do at the end, congruence to minus 1, and there, the negative 1 is going to be multiplied by itself, B minus 1 over 2 times. Then we have J squared, and again J equal 1 to B minus 1 over 2 mod P. Sorry, this is going to be actually, yeah, let me write this, and now at the end I put it also congruent to negative 1. All right, now because of the prime P is equal to, since P is equal 4K plus 1, then we have that P minus 1 over 2 is going to be 4K plus 1 minus 1 over 2. That's going to be 2K. So the exponent in here, so this implies that the negative 1 to the P minus 1 over 2, this is going to be negative 1 to the 2K, and this is equal 1. So now we have this. So we have the pi as the multiplication of these numbers. Well, and now by Wilson's theorem, the other part of the congruence, this is congruent to negative 1 mod P. Now this product, it is the product of J squared. I could take the square outside, means I multiply the numbers and then square the result. So this means that this x equal to this, J equal 1 to B minus 1 over 2, is a solution to x squared is congruent to negative 1 mod. Because it satisfies the congruence, okay, in other words, this number square is congruent to negative 1 mod B. In fact, it tells you what the solution is also. In other words, this is a constructive proof. Now, let's look at the other way around and assume that we have the equation has a solution, and you want to show that the prime P must be either 2 or P is congruent to 1 mod mod 4, all right? So we're going to go this way. Yeah, we're going to prove this by contrapositive, okay, by contrapositive. So which means we're going to show if P does not equal to 2 and P is not congruent to 1 mod 4, then x squared congruent to -1 mod P has no solution. So this is what the contrapositive means, and it's equivalent to actually the statement that if this congruence holds, then P must be either 2 or this. Now, from here, P does not equal to this, and P does not, remember P is a prime also, then P must be congruent to 3 mod 4, because this is the other type of primes, all right, of the form 4K plus R, all right, either to be a prime is 2, or 4K plus 1, or 4K plus 3. All right, now let's assume that if x equal a is a solution to x squared congruent to -1 mod P, then of course it satisfies this. A squared is congruent to -1 mod P. All right. Now let's look at a to the power P minus 1. So we're going to raise so we have a to the power P minus 1. Can say this is equal actually a squared to the power P minus 1 over 2, right? So the exponent. And now this is congruent to, because a squared is congruent to -1, then we have P minus 1 over 2 mod. All right, because this is congruent just to -1. And also because P, it's an odd prime, okay, because it does not equal to 2, so it must be odd. So this is congruent to actually -1 mod. Now, so this is this side in here, it looks like it's Fermat's sort of theorem in here, except we got a wrong congruency there. But in order to actually have this satisfy the condition in Fermat theorem, we must show that P does not divide, okay? So I claim that P does not divide A. Well, let's assume it does. Assume that P divides A. Then what does this imply? This implies that P definitely is going to divide A squared, and we also have the A squared is congruent to -1 mod P, which makes P divides A squared plus 1. All right, let's put these together. These two congruence relation, divisibility, sorry, then P divides their combination, a combination of this. So this implies P is going to divide A squared plus 1 minus A squared, which is equal 1, and definitely this is not a correct statement. Okay, so this is a contradiction, which means that the claim here is valid, so therefore the P does divide, actually it doesn't divide A, sorry, because we did it with contradiction, so this one is A, and hence the greatest common divisor of A and B is equal 1. One last step. Now we have, this implies by Fermat's theorem that A to the power P minus 1 is congruent to 1 mod P. Well, we have a problem in here. So we have this congruence in here, all right? And the Fermat congruence implies that 1 is congruent to negative 1 mod P. And this implies actually P divides 2. And again, a contradiction since P does not equal to 2. Okay, it's a different front. Therefore, this contradiction actually came from assuming the equation has a solution. So therefore, by the contrapositive, the equation, actually, if the equation has a solution, then the P must be either 2 or congruent to 1 mod 4. All right? All right, let's stop right here.